It's nice to see you again. I was here last year, and this year I decided to bring also my colleague, with whom we are working on one interesting project. We are part of Intel organization which is focusing on open source technologies. Specifically, we are working in a team which is working on cloud native stuff, and Kubernetes is one of our main topics. And well, just to be a bit more interactive with you guys and to wake up you after lunch. So how many of you are aware what Kubernetes is? Okay, good. How many of you know how resource management works in Kubernetes? Okay, well, few people who know probably will be able to learn a few new tricks here. So we are going to talk about the resource management, how it works in Kubernetes, what you can do, what you cannot do, what is the sum of underwater stones. And we actually want to do that in the way of, not just an abstract way, but trying to explain how it can be applicable to like real world problem. And the real world problem is like noisy neighbor. So of course, like all of us, we have like either neighbor with a drill overnight or evening. We have like drunk company in the cafe near you. But the same thing applies even to cloud workloads. So you have something what behave not as expected. So to explain why it is and how to treat it, we need to actually go down a bit to a hardware level, see like why it's happening, and how it's into Kubernetes, and what actually you tweak. And then, in the end, we will show you one of the projects what we recently open sourced, and we will have a demo about it. So, a noisy neighbor. The old days, when you have like one dedicated server and it consumed by one workload is already gone. So we got to VMs where you had like few VMs running. Nowadays we have hundreds of containers running on the node. And of course, like we think what we are trying to talk here is it's not going to solve all of your problems. Like all your workloads are equal in different shape, in different sizes, in different combinations. So it really looks like a Tetris. And we are not trying to play with Tetris on the level of a whole cluster. So for that, there are other means, like you have custom schedulers and so on and so on. What we are focusing now today is about the scenario of one single node, like what is happening on your one compute node. And if you're using the Kubernetes on top of some public cloud infrastructure, most probably, not all the things what I will tell you will be applicable because some of those hardware details is actually hidden from you by hypervisors what cloud provider is giving to you. So, again, a bit of interactive. So this is example of like most common used servers, like 2 sockets, 2 CPUs, some memory, some PCI devices, some interconnect between those. So how many of you think what is accurate representation of modern systems? Okay. You think it's not, right? But actually, this is how the Kubernetes sees the system. For Kubernetes, all the CPU cores are equal. All the memory is equal. It doesn't really care about interconnect. All the devices are equal. So when you say my workload wants to use 10 CPUs, it doesn't really care. Like it will allocate from one side and one from another side, and you will get something. But if we go deeper, so nowadays what we have is what inside the physical CPU, what you purchase in the shop or you get it pre-installed, you have one or more dies. And inside these dies, you have several cores. And all of those cores usually nowadays, again, have a hyperthread. So you have scenarios when you have multiple applications running on the same physical core. And because there is a first level of shared resources between like L1 and L2 caches, it's already like if you have two completely different workloads, you already started to compete against those resources. So if you have a performance critical applications, it's already good if you can say like, okay, this physical core is my application, please don't schedule any other applications here, we want to do something else. Our application should be running somewhere else. The next level is L3 cache. So practically it's when you're trying to leave the border of the CPU. So you are trying to access outside world between those few cores. And here again, L3 cache is a bit bigger, but again it's a resource which is highly competed by multiple processes, multiple applications at the same time. And luckily, in modern processors, in multiple vendors, you have a technologies actually how to control it per process based. So in Intel, it's RDT. In our vendors, we have different names. And the next thing is memory. So you have a memory controller, you have some limited bandwidth or limited speed, how fast you can access that memory. And all of this is so far linear. So meaning what, like unified memory access or uniform memory access. And this is something what was valid, well, 15 to 20 years ago. So you had set of cores, you have interconnect bus, you have a memory. And regardless from which core you access, it's constant speed, constant cost, just based on how fast is your bus. But that's not true anymore. So nowadays systems look something like that. So the current technology is to use NUMA, non-uniform memory access. So how it's different? You have a logical combination of set of CPU cores plus memory controller plus a local memory. And then you have some interconnect between all of those. And keep in mind what this is like two key things here. One thing is it's really logical, because in different systems it can be hidden by BIOS, by your system management board differently. And second thing, it's all about the memory access. So it's not really connected to devices, it's not really connected to how it's physically organized. It might have some commonalities, but don't assume what one physical socket equal to one NUMA node, or vice versa. So, going back to a real life picture. So, we have two sockets, we have a bunch of cores, and in reality, not all of those cores are equal. And we are not equal in different shapes. So you have technologies like Turbo Boost, where you have the different scaling. So based on how much you're active cores, it will be different frequencies. You might have a technology like Speed Select, where you have specifically say like those 5 cores run on higher frequency, and those are on slower frequencies, like ARM had it as a big little kind of scenarios. When you have interconnect, nowadays it's usually not a one. Like even if you have 2 processors and you have 1 connection, in reality it's not 1. It might be 2, it might be 3, it might be more. It really depends on your server motherboard, it depends on your processor, it depends on multiple things. And then NUMA nodes, as I showed, it's logical. BIOS can group it, what you have multiple in one socket. BIOS can say, like, okay, well, actually those who hold the 2 memory controllers on the same socket will become to 1 NUMA node. And then you have devices, and devices were close to particular core, even though the operation system Linux sometimes hide it behind like NUMA locality. And then with devices you have even more complexity, which I will try to avoid, but one thing which I want to show is what you have as integrated system devices, like network cards most of the time, hard disk, and so on and so on. So you also need to keep in mind what this is also becoming a bottleneck when you're trying to actually combine, like I want to use device, I want to use some cores, I want to use some memory, I want to use some storage, and so on and so on. So this overall picture is quite complex. And Kubernetes doesn't know anything about this. So what Kubernetes actually knows? In Kubernetes, when you are describing the workload, the minimum unit of what your description is pod. Pod means one or more containers. And for each container, you have a section called resources. And inside those resources, you have request and limit. So request is used in scheduler to see where I can fit, like to which node I can fit this workload. And limits just say like, okay, well, we fit in that node, but if you have some free capacity, allow the workload use up to this much. And in reality, Kubernetes knows only about two native resources, like the CPU quota and memory limits. It has a bit few more, but it's not relevant for talk today. What also Kubernetes have, it has some kind of quality of or class of service for the containers. And one of the problems with those COS classes were actually implicit. So you as a user of Kubernetes, you are not able to say what my container belongs to this particular class. What Kubernetes does, it actually takes this request and limits, the CPU and memory, both of those, and actually tries to calculate. So if request and limits are absolutely equal, it says like, oh, well, the workload knows what it does. We will do it as a guaranteed. If we don't match, but we do both specify it says like, okay, well, minimum request is that, maximum is that. So let's classify it as burstable. And if for some reason you don't specify those resources, it puts it into the best effort class, saying like, well, we can fit it practically on any node, but we can't guarantee what it will get at least something. And it will be forced to actually get evicted if some resources get needed for something else. So, minimal things, but what you do if you want to expose, for example, like I have a GPU, or I have an NER accelerator. I want to show it to Kubernetes. So the next thing what Kubernetes resource management support is extended resources. For those resources, you have already like fully qualified name. So you will have like vendor.com/GPU, and you will say, I want 5 pieces of this. Second thing is what you should have clear separation. What this is the Kubernetes one, this is the vendor at one. So you never should be using the Kubernetes domain for describing those. And those extended resources can be on two levels, the cluster level, and again, as I said, like here in this talk, we are trying to focus on the single node. And the extended resources on the node level. And on the node level, you have actually two options how you announce those resources. One way is you write so-called device plugin. And the one which does the discovery of devices, and when it says to kubelet, well, I have like 8 GPUs, those are names like that. And when kubelet will be tracking what, like, okay, if one container is using 1 GPU, it will say, well, I have 7 available to get the more workload to the same node. Another thing is arbitrary declaration of the resources. So you can use the REST API to control plane of Kubernetes and say, on this node, I have resource vendor.com/foo, and I have 20 pieces of it. So the scheduler will know what those resources are used, but the scheduler, neither scheduler nor kubelet, they will not do anything about those resources. It's just like pure counters. And I don't know if you probably noticed it or not, well, when I was talking, I was always using the integer numbers. That's one of, again, limitation of extended resources. So it's always counter. So you always declare, like, I have this much, and kubelet and the scheduler tracks use it this much. So what happens if you want to try to pass the parameters like priority or like some percentage of something? Well, the simple answer, you cannot. But there are a few workarounds. So one of the workarounds is using labels and annotations. Labels usually use it in the scenarios when you have something like really not countable. So for example, you have a node which has particular instruction set, for example, like AVX 512. And then you can say, like, use this workload only on the nodes which has that instruction. Annotations used in the scenarios where you have a bit more complex thing, like in this example, like for network ingress egress limitation. So you say what this set of containers will be limited or should be limited to 1 megabit of traffic, and you need to pass that information down to a CNI plugin which says, like, okay, well, we enforce this particular limit. But again, Kubernetes in some sort is not really flexible. So things like labels and annotations, they attach it to the level of the pod. And pod, as I said, it's one or more containers. So if you want to say, for this particular container, I want 1 megabyte or 1 megabit, and for that 10 megabit, you need to start inventing something. So all of those declarations, all of things what kubelet knows actually about the system, how it works nowadays. So we had few components which is quite old, like CPU manager, device manager, we have already for several years in Kubernetes upstream. We know how to discover a few things. We know how to allocate at least something. But we were not connected together until lately. And in this release of Kubernetes 1.16, which was released like a week or so ago, the new component came to the picture, the Topology Manager. And what it does, it actually takes the hints from both CPU manager about the current system, it takes from device plugin information, and then tries to combine, and then it says, like, yeah, well, if this pod we want to admit to the node, this is the optimal configuration what you can fit. But again, Kubernetes tries to be really vendor and hardware independent. And because of that, the hints what in current form exist, it shows only in the terms of NUMA node. So again, if you try to say what I have a device which needs to be used with particular set of cores, with particular CPU, for example, with higher frequency, you cannot expose that. So again, you need to invent something. And to invent something, you need to go down to a stack. And you need to see like how components are talking to each other. So the first component is kubelet, where your pod is arrived, and when it talks to level below the container runtime. And this container runtime, it's specified by this CRI interface, which has a simple commands like start container, run, stop container, and this is configuration of a container, and so on. And this is the information what kubelet able to tell to the down level. So you can see what, like, you have CPU, quite good settings, but in memory, if you noticed, it only communicates about limits. It's already lost the information about requests, what you have specified. And then for CPU and memory placement, it has two fields. But in reality, it's either completely not using it, or it uses only CPU set. Memory set is not used at all at the moment. And then if you go down, so you have container runtime, like CRI, containerd, Docker to some extent. So you go down and you have actual implementation of component which does actual containerization. So it's so-called OCI spec, Open Container Initiative. And one of the most commonly used implementation, it's runc. It was part of a Docker. Nowadays, it's part of like default runtime in anything else. And it has a bit more information. So you already can say on block IO level what like this task has a bit more priority, this set of containers a bit less of priority. You can do memory reservation. You can do like memory CPU real time. You can limit kernel usage. You can also do changes towards the cache and memory bandwidth. But again, it's one of the implementation, and it's not implementing fully the stack of the changes. And if you look at the OCI spec itself, there are a few other parameters which is hard to expose in command line utilities like runc. So one of the things is like block IO. So you can define also not only like relative priority between the containers, you can also start to say, well, on this storage device, you have a full bandwidth. On this storage device, you actually limit it to, I don't know, like 1 gigabyte per second. Then huge pages, again, right now, the spec has it. CRI interface doesn't have it, but the Kubernetes supports the huge pages. So how it's done, it means that the kubelet ignores the whole chain of command. It just goes and directly changes something in the C groups, which sometimes leads to quite interesting errors. And a similar thing goes to RDT class. So in case of runc command line, you have ability to say what, like this is exact schema, but if you try to use it on many containers, you will soon run out of hardware support of classes. So at some point it will say like, sorry, you already created so many classes, I cannot handle it anymore. So the spec supports things which command line utility doesn't. But other good thing, what is part of the spec, and runc knows about it, how to execute it, but again, a bit more complex to use, it's so-called OCI hooks. So OCI hooks were called during the lifetime of a container. So before it starts, before it stops. So you can enforce some parameters before or after like workload. And to do that, you have few options. So if you look at the whole stack, so you have a kubelet, which gets the whole information and talks to container runtime, cryo, containerd. And then on those, you have so-called runtime classes. So you have default runtime class, which is usually runc, and then you can have multiple hours. And for those runtime classes, you can say, well, actually, run my patched version of runc, which will know something about more. For example, like it can get the annotation about the priority of block storage and enforce it in the kernel. Or if you are lucky and you are using cryo, you can say, well, run this press start hook, and inside the hook I will get exactly the same information as runc, so you don't need to hack runc, you just put your small script which writes something into C group FS. But our problem is what not all this container runtime exactly the same. So cryo is good, it passes all the information, it allows you to configure the hooks. But containerd doesn't. It filters out a lot of information. It doesn't allow you currently to configure the hooks. So we need something else, like if you want to do something complex. And we looked at this picture for a while, and we decided, okay, well, why not to go here? And this is where we have a project. We recently open sourced it. It's about like a couple of weeks. It's a proxy. It stays between the kubelet and actual container runtime. So it allows us to actually intercept everything what kubelet says to underlying levels. We can do some tweaks. We can do some instrumentation. And what actually it allows us to do is it allows us to experiment with Kubernetes resources without touching the Kubernetes itself. And we organized it in a way what, like the code, the policies of the Kubernetes can be easily extracted into this external component, and once like modified, tried in production, and if we are ready to propose it to upstream. So, like, it allows us to help with instrumenting and hacking based on your own requirements. And the project is on GitHub. You have a link and slides what will be published. You can look in more details. And now I would like to give word to my colleague who can go a bit deeper.
Hello. So I take over from Sasha. So next we are going to take a look at briefly how Sierra Resource Manager fits into this whole picture. So where it is on the node and how is it related to kubelet and the container runtime. We will take then a short look at what is the current feature set and what we are having in the pipeline, something that we are working on and hopefully soon hitting GitHub. And then finally we are having 2 screencasts of 2 demos, which are demonstrating some of the existing capabilities using 2 simple policies. So if we take a look at the architecture, so you can see that, so first of all, Resource Manager is collecting a lot of information, and for observability, it is exposing those for consumption to external entities. So naturally, we are doing some logging, then we are collecting basically IPC traces, how information is passing through the Resource Manager, and a lot of metrics about the node and the containers that we are managing and making those available to external components. Then you can see that the Resource Manager basically, as Sasha mentioned, it is a proxy sitting between the kubelet and the actual container runtime. It is intercepting requests as they are flying by. It does some local processing using the policy engine and the actual policy logic. So basically local policy decision making. And then it is putting those policies into practice. So in other words, enforcing those decisions. Now enforcing those decisions can happen in a number of ways. The simplest way is that we are simply mutating, so modifying some parameters of the request that we intercepted before we are sending it forward. So basically forcing some changes to what the kubelet was asking for. The second way how we can enforce some of the policies is that we are generating actually requests of our own and sending to the container runtime. So basically container update requests. Third mechanism is using libcontainer or some other library and the available kernel interfaces. We can enforce additional policies which are currently not supported by the container runtime. The Resource Manager also exposes the resource assignments that it assigned to each container, to the container itself, in a simple way. So basically we have something called a resource file, which is just a file under a well-known path, which is mounted inside the container's file system, and it is always updated with the latest up-to-date information about the resource allocations for that particular container. So if, for instance, the container needs to adapt itself to the current resource allocation, it can with inotify modify this file, monitor this file, and receive notifications about changes. Then the Resource Manager also keeps up-to-date cache about all the pods and containers in the container runtime. This cache is made available to all the policies, so this is how the policies are making their decisions. They acquire information about the containers and the pods from the cache, and this is how they also actually publish their decisions, by doing changes via the cache-provided interface to the containers. The cache information is also exposed to external components. So we are having a configuration and external policy API, This interface is used to download configuration and configuration updates for the policies. So for instance, how we are using it, we are keeping our policy configuration for every node in the cluster as a Kubernetes config map, and that config map is basically downloaded and put the cache and then made available to the policies. Another purpose of this interface is that although we have a number of built-in policies, we do not think that we will be able to come up with all the necessary policies for all interested parties. So we would like to make it possible to externally plug in similar policy decision-making logic with similar capabilities without having to actually integrate and compile it into this whole engine. So if we go forward, so what do we have currently in the resource manager? So we have a number of policies, actually a little bit more than we see here, but these are the relevant ones for this discussion. So we have the static policy. That is merely a demonstration of how you can lift out an existing policy from the kubelet, and with relatively small modifications, you can adapt it to the resource manager infrastructure and get it working there. It is equivalent in functionality to the static CPU manager policy in the kubelet. Then we have static plus. That is inspired by the static policy, but it has a couple of additional features. We will see that in the demo. And then we have the topology aware policy, which is currently our most complex policy. So that one tries to perform a hardware topologically optimized container placement within the node using runtime discovered system topology information. So what do we have in the pipeline? So Intel RDT. So in addition to these, currently we are controlling mostly memory and CPU. What we would like to have is using Intel RDT, allow the policies to have fine-grained control over cache allocation and usage and memory bandwidth allocation and usage for the containers. The block I/O, So the block I/O classification and tuning, that is basically the same as Intel RDT, but for block I/O. So we are using the BLK-IO C group controller to allow the policies to have fine-grained control over how much I/O a single container can do. Better monitoring and resource usage, and dynamic rebalancing. So currently what we do is that, so we only make changes to the container resource assignments when a new container is either created or destroyed. This is good enough as a start, but we need to do better. So what we want to do in the future is also dynamically monitor how much resources the containers are using, whether there is resource contention between the different containers, and then if we notice that something is a bit off, we act and rebalance, basically recalculate again, and not just when containers are coming and going. Dynamic configuration and policy API. So currently it is not possible to externally plug in a policy. And this is something that we want to enable people to do, because again, we do not think that the policies that we will have there will be satisfactory for everybody. So we have two demos, and I will try to, so these are screencasts, which I cannot pause. So I will try to explain what is going on and keep up with the demo, but I think it will be a little bit difficult for me. So I encourage everybody who is interested in the details to check out in peace and quiet for yourself in an environment where you can pause it and see the explanation which is in the screencast, which is trying to tell what is happening and why it's happening. So let's first take a look at the static plus. So the static plus policy is basically an improved version of the static policy. It can do shared, exclusive, and isolated allocations and mixed allocations. So these are basically about what kind of CPUs you are allocating to a container. So we have a single node cluster with some isolated CPUs, a two-socket system with subNUMA clustering enabled, so we have 4 NUMA nodes. We have a couple of YAMLs for these demo pods. So here is the first one. This is a shared allocation. So if you see, sorry. So basically, the shared allocation is about a container which does not need exclusive resources, so it is going to get assigned together with other containers to a shared pool. That's the most simple case of all. That is what we are taking a look at first. Then exclusive, where you basically dedicate exclusive CPUs to a container. Then we take a look at the isolated one, which is equivalent to the exclusive one, but you are using kernel isolated CPUs. And finally, a mixed one, when you need a mixture of shared allocation and either exclusive or isolated ones. So here you see that there is a 100 milli-CPU request, so not a full CPU. The exclusive one is asking for 3 CPUs. So basically, it wants exclusive usage. It's a guaranteed QoS container. This is the isolated. It's otherwise the same, but it opts in with an annotation for isolated CPU allocation. And then we finally have the mixed one, which is trying to take 3.5 CPUs. So it should get half a CPU worth of shared allocation and then 3 exclusive or isolated ones. So we create those pods, or pod with 4 containers. All of them are running. So this is the resource file. So the shared one, you can see that it only got shared CPUs, basically. And it happens to come from all the NUMA nodes. Then the exclusive one, well, it got exclusive CPUs. Isolated one, well, there were enough isolated CPUs free in the system, so instead of exclusive ones, we are allocating them isolated ones. And finally, the mixed one. So there you can see that it got assigned to the shared pool of CPUs, and it also got dedicated isolated CPUs, because we still had 3 left in the system, and it was asking for 3.5 CPUs altogether. So that's about this demonstration. So the next one is about the Topology Aware. So the Topology Aware policy is more complex. It is trying to do a topology fitting of the workloads on the system using the hardware topology information that it discovers during runtime. It is also using so-called topology hints. So basically, that's device affinity of the containers. And it also can use annotations for intrapod container affinity and anti-affinity. So basically, if you want to put together containers or far away from each other, these annotations you can use for this. So this is our hardware looks like. So you can see that we have 4 NUMA nodes because we have 2 sockets and sub-NUMA clustering enabled. Similar setup, we have some isolated CPUs, so we could do isolated allocation. We have the manager running. So simplest case, basic fitting. So what happens when we have a small allocation that fits into a single NUMA node, so as close to the hardware as we can. So this is how it looks like. We are trying to create 4 containers, all of them with very small allocations. So what should happen is that because all of them fits together, or fits into, there are 4 of them, there are 4 NUMA nodes, so we should spread, the policy should spread those around equally. So basically everyone should get allocated to a different NUMA node on the system. So first one gets to NUMA node 0. Next one. Okay, that allocated to the same socket, but NUMA node 2. Third one. So CPU socket 1, NUMA node 1. And finally, CPU socket 1 and NUMA node 3. So basic spread out algorithm. Okay, we delete the pods. Next, we take a look at the device alignment. So device alignment is interesting in the sense that there will be one container which wants to use a block I/O device, and that block I/O device happens to have hardware locality to NUMA node 0. So what we will do is that we are going to load first the NUMA node 0 with an unrelated container. Then we are going to allocate another container, and then we are going to finally allocate the one which has NUMA node affinity because of hardware. And this, everything works correctly, despite the fact that NUMA node 0 is already the most loaded node in the system. It should get allocated there because the node has still spare capacity to fit the container. So here is the YAML. So we have a host path, which is, as you can see, so it's a SATA block I/O device. And we will see in the next one that it has NUMA node locality. So once we create it, we dynamically detect that it has NUMA node locality 0. Okay. So we unfortunately ran out of time, but so if you are interested in these demos, you are welcome to watch the screencasts. Thank you.
Yeah, it's really sorry what we messed up this time a bit. So we don't have time at the moment for the questions, but we are happy to talk in the corridor or just catch us during the conference. We are really interested in your feedback, and I would like you to invite both to our project and one in Kubernetes upstream in Signal discussion. If you have some use cases, if you have some ideas, please join us. And people are becoming more and more interested in hardware-specific or some cloud provider-specifics inside Kubernetes.
Okay, let's thank our brave speakers who really used up their time slot up to the last second.